Today, we would like to walk you through a use case. The last few weeks, we've covered various ways to leverage the RapidMiner platform to do data analytics and machine learning. Today, we want to apply it to a specific use case around predictive maintenance. Why do we want to do predictive maintenance? Well, we know that scheduled maintenance is important for any type of piece of machinery, whether it be aircraft, vehicles, what have you. The challenge comes, however, sometimes these vehicles break down outside of a scheduled maintenance window, and it becomes very costly for us in terms of just lost revenue, also just delays in terms of getting parts in and things like that. So there's a way we can identify where these delays are likely to occur and get ahead of them outside of a scheduled maintenance window. We can significantly produce or increase productivity and reduce downtime for our equipment. And the way we'll do that, we're going to leverage a series of historical data that we have from our data sets. So let's jump right into the solution. What I first would like to start you off with is just kind of a high-level overview of what we're going to cover for this particular session. And as you see, we're going to do a predictive maintenance, this time on a turbofan. We'd like to determine when this is likely to fail. And we have a bunch of sensors, 21 sensors, in fact, that measure things from such as fan speed, vibration, temperature, pressures, etc., are all being measured on these 21 different sensors. And we've collected this across a series of engines. And I want to see if there's essentially a way we can identify where those failures are likely to occur, or more importantly, when they're likely to occur. So we can bring the engine in for unscheduled maintenance prior to a catastrophic failure. And how do we go about doing this? Well, let's start off first with our RapidMiner platform. We're going to jump into AI Studio and first actually take a look at the data set and look at how we can actually begin cleansing it, combining it, and then building a predictive model to apply on top of it. Let's first start with our data set. To mention today, we have a data set that contains multiple sensors, 21 in fact, and I can take that data set and connect directly to it. We've covered this in previous sessions, how to connect to various data sources, whether it be from an Excel file, a CSV, a database, or even from various applications. We've touched on that before, so suffice it to say, this can be any source of data. In my case, I'm just pulling from a flat file, but you could, in fact, pull or connect to data from any source that you have to load into our view. I'm going to go ahead and run this so I can just get a quick preview of the data. And as I mentioned before, you can see I have those 21 different sensors that are listed. I also have the actual engine number and a time cycle. These two things in combination are what's going to tell us the actual status of the engine. So, for example, engine 8249 at time cycle 1 is most likely going to be in the OK state, but potentially in cycle 300, it may have encountered a failure. So you can kind of think of the engine number and the time cycle as kind of a unique key combination to identify a record within the data set. Now, if I want to just inspect my data a little further to see if there's missing values, to make sure data is within a set range, etc., I can take a quick look at the stats for this data set. What I can see is for my 21 sensors, they all are listed as real numbers for the data type. I have no missing values for any of these. And again, I can see sort of the range for these as well. Now, if anything is outside of the norm, you being the domain expert, you can look at these and realize that potentially our fan speed sensor might be somewhat out of tolerance, out of range. You might want to go and just verify the actual data, make sure there's no outliers or anomalies within the data set itself. In my particular case, this all looks great. But one thing you will notice is that while I do have the engine number and the cycle time, along with the sensor data, there's no actual status here of actual good or bad. So I have no way of actually building that predictive model. So the first thing I want to touch on here is how I can combine this data set with the actual status of the engine at a given time cycle. Lots of ways we can do this, but again, turbo prep is probably one of the easier ways to go about blending, cleansing, normalizing, and preparing data overall. So I'm going to just jump right over to turbo prep. And I'm going to look at those two data sets. So you notice this one should look fairly similar to what we just saw a second ago, all of our sensor data, along with our engine number and our time and cycles. Okay, and then in my status data set, notice I have that same engine or unit number and that time and cycles, but now I just have a status column that's listed. Before we combine these, I want to just kind of inspect this as well. In my data set, I should only have two different statuses. It should be either okay or bad. I just want to verify that. Again, if I see something outside of what's expected, indication that I might want to do some additional cleansing to my data set. So a lot of ways we can look at this. I can look just from the histogram across the top of this to see the distribution of the data sets. Or if I hover over, I can see a breakdown of the actual values. Or to make this even clearer, I can just show the details for this given data set. And now I can see in my data set, I have quite a few that fall into the OK status, around 97% actually, and about 3% that are bad. So right off the bat, you might notice that this is a highly imbalanced data set. Might want to do some additional work to make sure we don't have an overfit model in this case. But this gives us really just a clear indication to look at our data set, identify where sort of the gaps might happen to be, or if we need to do some additional cleansing, we can. Things like transforming our data set, where we can do things like filling and missing values, changing data types, filtering values, splitting or partitioning data, etc. All those types of cleansing steps we could perform here. I can also do a series of cleansing steps, create my own custom functions or expressions if I need to, generate pivot tables. But as we saw, our data set's, again, fairly clean, so not too much prep that needs to be done to it. I really just need to combine these two data sources together into a single report so I can use it for my analytics. So let's do that. I'm going to click on that merge button, and I'm going to tell it first the data sets that are of interest. So I'm already working with our sensor data as my left table, and I want to combine that with that status table as our right report. I then can tell it the type of join that I want to perform. In my case, I want to do an inner join, meaning I only want to see records where there's a corresponding match in both the left and the right table. And then finally, I want to select what my actual joining keys are going to be. If you recall, I mentioned the unique combination of the unit number and the time and cycles is going to be our key combination. So I do need to actually include both of these as my joining key. So let's go about doing that. We'll first do our unit number from our left table. Now notice once I select the left table attribute, when I click on the drop down, I'm going to be presented with most likely attributes that'll match from our right table. Notice I have some of these that'll have either 0%, meaning that there's not a likely match to the data set itself, or I have some that just either the data type doesn't match or the attribute itself doesn't have the resulting match that will produce an output table for me. However, I do see unit number here is actually telling me that these two are actually good matches as a joining key for this. Again, in my data set, these are named exactly the same, so it's not that big of an issue. But we do see scenarios where you're pulling data from different data sources where attributes might have different names. So this just, again, kind of guides the user a little bit, even if their attributes do have different names, to which one is the proper joining key. So I'm going to select that. And as I mentioned, I have actually two keys that I want to join on. So I'm going to, once again, select add join. And this time I want to use the time and cycles as my secondary key. Similar to before, I'm going to get that indication to say this is most likely the correct key to join on. Once I have them both selected, I can just update my preview, and I'll be able to see the full data set. Now I can see the purple columns would represent the join keys that I've selected. The blue columns will represent the data from my left table, in our case, the sensor data. And then the final column here in green, this will be our actual status column. So I now have this all in one combined data set. I can see I have just over 265,000 records. And this looks the way I want it to. So I'm going to just commit the merge that's here. And I'm fairly satisfied with this process that I have thus far. If I did need to make additional changes, I could in any of these steps. And if I want to see the changes that I've applied, I can take a look at my change history and see what was done, or roll them back if necessary, etc. In my case, I'm fine with these, so I want to go ahead and commit these changes so I can reuse them if I need to down the road. So I'm actually going to just add this to the process. Now notice when we first created our process, we had just this initial step, but even though I leveraged the turbo prep, it's going to take all of those steps for me and generate a series of operators. Notice this is a stack operator, meaning I can actually go inside of this and see the sub-processes that are being created. Let's do that just briefly. If I double click, I can see all of the steps that took place from one loading in the status data set, just doing some understanding or rearranging of the data, the join that we actually performed, and the actual final output that we've created is all processed for me. I show you all that to just say, just because you're using turbo prep or the auto model, which I'll show in a second, these are not black box solutions. You can always go back and configure or modify anything that was created by the turbo prep or the auto model. But now I have a completed data set that has both my input variables with my 21 sensors, along with my output, the actual status for those engines combined into one single data set. So now I actually want to begin building that predictive model where I can use the data to predict when an engine is likely to fail based off the combination of values that we see from these 21 different sensors. Similar to what we did before, where we used turboprop, this time I'm going to use the auto model to automatically begin modeling my workflow. We have a bunch of historical data that's labeled, and we want to use that historical data to predict the outcome of a new engine given a given a series of inputs. So for that, we'll do a prediction. And the thing we actually want to predict is going to be that status column. So I'll just select that, and then I'll select next. Again, we saw this from before when we looked at our data set in the turboprop, the distribution. So we're kind of familiar already with this breakdown. But if you did want to either clean or need to make modifications here, you could. Or if you just wanted to rename the actual attributes, you could as well. So right now we have our engine status is okay or bad. Maybe I want this to actually be represented as fail, and the good status to be listed as good, or something to that effect. Again, you have the ability to kind of map these as you so desire. Even in scenarios where you have more than the two, and you only expect it to be binary, you can actually group or combine those attributes by giving them the same name. So this screen is very flexible in that regard. While we're not going to use this today, you can also assign a penalty for incorrect predictions. So to kind of force your model a little more to make the correct prediction when we're working on it. Again, you got to be careful with these values. If you put these too high, you could potentially have another overfit scenario. So you do want to be careful with how you leverage these, but this is a good way to just add a penalty cost for incorrect predictions or add a positive cost for correct predictions, even for that matter. Okay, so let's go through next again. We're going to go to our input selection. So we had those 21 different sensors, but in reality, not all 21 sensors are going to be have any sort of predictive power. So what we'll indicate for you here with our quality indication is which attributes are likely to have high predictive power with the green indication, which ones have okay or marginal power, which would be in yellow, and which ones have little or no predictive power in red. Now, again, you may have to include some of these attributes for your own individual analysis. You as the domain expert, you can always overwrite what's selected for you by the auto model. These are just our best predictions based off of best practices that we'll see in a predictive workflow. But you can, of course, modify or change any selection that is here. And then the final thing we'll do just before we get to our models is we want to select which model we want to run. Generally speaking, I would recommend selecting all of these and just letting the software kind of rank them for you. In the interest of time, I am going to select just a couple of these so we can see the outputs from them. But when you first run this, I would generally select kind of running through all of these. Or if there's a specific model that you are interested in, you can let the initial workflow run in auto model and then go and modify it after the fact. Okay, so let's go ahead and run this. And like I said, this will take probably a minute or two to run through each of the different data sets. Notice, even though we have 3 models listed right now, as we iterate through, you're going to see this number go above 3. And the reason for that is, if you saw on the previous screen, we had each of these set to do the automatic fine tuning. What that means is that it's going to look at each of the individual models and it's going to adjust a series of parameters in those models and select one that has the best performance overall. So even though in this case we have 3 that are selected, we'll see kind of a significantly higher number that will be present for us at the end. We do want to let these other 2 finish, but since the naive base has completed first, let's just take a quick look at some of the information that's provided. Out of the gate, we can see our classification error. Since we are doing a prediction, we want to see how many did we predict correctly versus the actual value, and that's just what this value is representing for us. Essentially, this model predicted 3% incorrect, essentially is what this is telling us. We can, of course, change the metric that we're using. So if I want to look at the accuracy percentage instead, for example, or if I want to look at precision or recall, I'll have the ability to verify those results here. What we'll also see is a few different data points as well. So things in terms of how long it took to actually run and test all of the components of the model, how long it took to train the model, and then how long it takes to score new inputs. This last one is of most importance for you, especially if you need a low latency type of model that can rapidly score data, generate, send the predictions back to you. We kind of want to err on the side of a lower runtime. Of course, some of these other metrics are going to be more important, but what I mean by that is if you have two models that have relatively close error rates, the other metrics look fairly the same. There might be one model may slightly outperform the other, but they're relatively close. But you have one that has a significantly lower scoring time. You might want to take the model that's slightly less performant, just by the nature that can score a little faster. Again, it's going to depend on what the model is used for and if that low latency is required. But suffice it to say, that is an option that you will have. Okay, this is just kind of the high level for the individual, for the group of models, but we can also look individually at the models. So let's take a quick look at this decision tree, just for example. I can see the model itself. In this case, I can see the full tree. If I want to follow any of these nodes down, I can essentially have sort of a root cause analysis to determine what's likely to cause a failure or not. And I can start at any point. So for example, I'm looking at sensor number 9. I can see if the sensor 9 is less than this value was at 920. It's going to follow this path, and you can just kind of follow the nodes all the way down to the terminal node and determine if you have a good or a bad result. So again, just a quick way to kind of validate the metrics that you have. From a performance standpoint, we saw this on the overview screen, but this just gives you all of the performance metrics on a single slide for you to kind of compare the model itself, make sure it's performant for you. If you want to look at the predictions themselves, I can see what the actual value was versus what was predicted and what our confidence was. So this just gives you a good sense of how well the model is performing. And then finally, for the simulation, I can take a look at the simulator and see what will happen if I were to, for example, change one of the sensors. So we see right now sensor 13 has a huge impact on a failure, essentially. So basically, as sensor 13 goes up, the model is likely to show a failure, essentially what that's telling us. And if I want to just kind of test that out, I can just modify sensor 13. Maybe if I slide that up a little bit, you'll see I'm still in the good state, but you see instead of being fairly confident in it being a good engine, now it's almost close to 50-50. We're getting to that point where it's, essentially getting close to that failure state. But you can do that for each of these different ones, just kind of slide and do kind of a what if analysis to see what ranges or tolerances might be beneficial for you for your given model. While maybe not applicable for this particular one, think about scenarios where you do have a series of controls. I think you set a machine to a set temperature or range or something to that effect, and you want to know what the most optimal settings are for that to produce the least amount of waste or to have the most use out of a component. Well, that optimize option will do just that for you. To go through each of the parameters and determine what's the most optimal settings for a given process that you might have. Okay. And then the last thing I want to just touch on here is that once you're inside of any of these models, again, just like we saw with the turbo prep, this is by no means a black box. If I want to see the actual process itself, potentially make changes to it, I can do that. So let's go ahead and open this up. And just as we saw before, I can see the full workflow that the auto model created for us. And of course, if I want to go and see any individual component, I can just drill in to any of these. I can modify sort of the parameter selection that's being made here, or I can modify the underlying model as a whole. So you still have complete and total control over how this is generated for you. But the auto model is again a great way to just do in a low code fashion to extract the data, do the appropriate model testing and validation, and showcase the best model for you. And now that I have the model selected, I can now put this into production, as we talked about in our previous sessions on exposing our models as endpoints and integrating this with either another application, a front-end GUI, or just having data automatically scored for us. Whatever the deployment mechanism might happen to be, this gives you a really seamless way to take a series of data sets, cleanse and normalize them, get them in an analytics-ready format, and then apply a series of models on top of that cleansed data, generate the best performant model, and extract it out to use in a production environment. With that, that'll conclude today's presentation. As always, if you do have any questions or would like to learn more about the predictive maintenance use case or just the RapidMiner platform as a whole, always feel free to reach out to us. We're happy to dive in deeper on any of these topics. With that, thank you all and have a wonderful rest of your day. Thanks much.